Hello, everyone, and welcome to our first of 5-part series, Explore Lincoln Laboratory Facilities, Microelectronics Laboratory. The MIT Lincoln Laboratory is a Department of Defense federally funded research and development center. Lincoln Laboratory is operated on a no-fee basis by MIT for the benefit of the nation. They approached $1.5 billion in research funding last year, more than half of MIT's total research. Lincoln Laboratory employs more than 4,000 people with their main site in Lexington, Massachusetts on Hanscom Air Force Base. The Microelectronics Laboratory is a facility within their Advanced Technology Division of about 450 employees. Now, please allow me to introduce our esteemed speakers from the Microelectronics Lab. First, we have Dan Pulver. He is the Microelectronics Laboratory Group Leader and leads a team of 65, where he developed Lincoln Laboratory's ISO 9001 certified quality management system and earned trusted supplier accreditation for custom microelectronic circuits. Previously, he directed fabrication operations at Luminous Devices and managed semiconductor production at Corning Lasertron. Dan holds master's and bachelor's of science degrees in electrical and chemical engineering from Rensselaer Polytechnic Institute and has experience in startup ventures and investments. We also have Carrie Huguenin, Associate Group Leader at the Microelectronics Laboratory. She joined Lincoln Laboratory in June 2023. She also has a master's and bachelor's of science degrees from MIT's Department of Materials Science and Engineering. She brings over 3 decades of experience in microelectronics fabrication across industry giants like National Semiconductor, Intel, Skyworks Solution, and Raytheon. At Intel, Carrie was instrumental in developing the polysilicon gate for the first Pentium processor. She later directed manufacturing quality at Skyworks during a period of rapid growth. Carrie has been actively involved in mentoring the STEM programs throughout her career. As a dedicated professional and mother of 2, Carrie is committed to advancing technology for the betterment of society. Now, before we get started with the presentation, I just want to steer your direction to the questions box. Please feel free to utilize the questions box to submit any questions you have throughout the presentation, and we'll try to address these at the end of the PowerPoint. Now, with further ado, I'd like to invite Dan and Carrie to share more on the Microelectronics Lab with the audience.
All right. Well, thank you so much for the warm welcome and the opportunity to speak today. The presentation that we put together has 5 sections. We'll move forward to the agenda slide. Thank you. So we've got 5 sections, a short video, and Dan and I have decided to swap back and forth so you don't have to listen to just one of us speak, and also because the awkward exchanges between my and his sections will humanize us and make us more approachable. So first off, I'm going to cover the facilities, a little bit about Lincoln Laboratory, and our buildings here. Then Dan's going to go into our fabrication technology enablers. Then I'll go back into device technology nodes, our capabilities there. Dan will talk about operating model aspects, and then we'll end on collaboration and how to work with us. All right, next slide, please. Okay, so a little bit first about MIT Lincoln Laboratory. So she did the introduction. We were founded in 1951, and the mission is a bit broader than it was initially. I think originally it was just air defense, but it's been technology and support of national security for quite a while, and I think it's very fitting. The laboratory really sees its role as being forward-looking regarding security architectures, really sees prototyping as being a key aspect of our work, and the development of advanced technology. Those are the key roles that we see ourselves in. The images here cover what we do here in the Microelectronics Laboratory, that there is this focus on advanced electronics. And it was already said that Dan and I are both part of Division 8. Lincoln Laboratory has 9 divisions, and each division is made up of groups. So Dan and I are one of 6 groups in advanced technology, which is Division 8. So you might hear me say Division 8 at various points. That's our home division within Lincoln Laboratory. Next slide. So we will talk about the microelectronics prototyping facilities. So on the left, this image is the MEL. So it's shortened to ML, but we all say MEL lovingly. So it is, the tagline for us is that we are the US government's most advanced captive silicon-based fabrication facility. The building was built in the early 90s, I believe 1991. And I think it opened in 93. I'm not sure if I got that right, but I think it's close. It is 3 floors. There's a fan deck up top, then there's the process level and a sub-fab below. It's over 18,000 square feet of clean room space, a mix of class 10 and class 100 space. We have over 60 staff, full-time staff, that are responsible for process and equipment health, the maintenance of the facility, as well as the processing of our wafers through the facility. So to do that, we have several roles. We have process engineers who are responsible for the unit processes that we have in the fab. We have equipment engineers and equipment technicians who are responsible for the maintenance of our tool set. And we have we have process technicians who are responsible for actually running the material through the processes. The integration function that you see in most fabs, that is a function that's actually external to our group. That linking of our unit processes together to meet program needs to actually make devices, that is owned usually by members of the other Division 8 groups, sometimes by people in other divisions, and sometimes by our external partners. So that's where we have to partner, is the integration. We run Monday through Friday, 3 shifts. So we're 24 hours a day, 5 days a week. And we're an 8-inch fab. I think I missed that point. We're an 8-inch silicon fab, so 200 millimeter fab. The picture on the right is the compound semiconductor laboratory and microsystem integration facility, lovingly referred to as CSL-MIF. It's probably the world's worst acronym ever. But CSL-MIF is in construction right now. It is no longer a single pile of dirt. It is now several piles of dirt. And we are hoping that it will proceed quickly to completion. We're very excited to have this new building. As you can see, it's going to be double the size of the current facility. And what the basic plan for the use of this lab is that we're taking 62 existing labs that are sprinkled throughout the current campus in various rooms and consolidating them into one space. And you can understand how that's going to help with maintenance and visibility of the tools and utilization of tools, and so many benefits to having a centralized facility. On to the next slide. So this slide is a 2D construct that is kind of similar to the Valley of Death slides, I think, that many of us have come to see frequently in the ME Commons slide decks. So here, the vertical axis is the flexibility and diversity of your technologies. So this would be novel materials, novel processes, maybe irregular usage of your tools and minimum controls, but great flexibility. The horizontal axis is your process complexity. So this would be the need for manufacturing disciplines, for process controls. You would have to have some barriers to change, so your process just isn't changing day to day, that it has stable inputs. And this is usually, to the right, would be needing usually for products that require a higher readiness level. So if you click the animation, you'll see the thing that's in the top left, where you have the most flexibility, but the least of those controls would be the university setting. And then if you click again, the far right is more your commercial fabs. And here we included the Fab Owners Alliance fabs. And we are part of the Fab Owners Alliance, which is wonderful because we can do a lot of benchmarking with them in regard to our own attributes of our fab versus the commercial fabs that are out there. And then if you click it again, we appear in the middle, bridging that gap between the lab and the fab. And these are our two buildings that you just saw in the previous slide. I think that this is kind of one of the themes that you'll see come up several times in this presentation. It's really important that we do have more of the controls like a commercial fab, but we have the flexibility, or at least almost as much flexibility to try novel ideas with some limitations on our contamination controls and such. On to the next slide. All right, so this is when I hand off to Dan.
In the video.
And I think the first thing is the video.
So there's a couple array of our lithography platforms. So for projection systems where we need masks, you can see we talked about the 193 nanometer scanner on the top left panel. The Canon stepper, we have two of those, a 5x reduction at 248 nanometers, which we do down to 200 nanometer work, kind of sub-micron to 200 nanometer line widths, and then a wide field 365 nanometer mercury arc lamp sourced tool called the IW. And we can mix and match across all of these platforms with themselves to make large devices. And for rapid prototyping or for finer lithography on the bottom, we've got direct write systems. So we've got a good Wraith electron beam lithography system with a 10-piece part holder for automated loading and overnight and weekend long processing, because it's not that fast. It's a single beam that's got great resolution, but it's only one beam. And then we've got a couple of direct write laser systems from Heidelberg, a digital light projection kind of mirror type one, the MLA 150 in the lower right, and then a microscope lens-based system that can get down to pretty good resolutions for optical lithography. We've printed 300 nanometer lines with that. So we've got a great versatile set of lithography tools to base it on. So that's a distinguishing factor of our facility. And then if you continue, the other thing that really distinguishes us, here's more lithography. Besides just printing simple patterns, we can also print 3D structures using grayscale lithography. And so if you give a partial dose, you can thin down the resist. And if you do sub-resolution features in your mask, you can advance. We can make complex surfaces. Next panel, on this compact spectrometer, you can see that the different angles we can form on a blaze grating to make a very compact spectrometer. And if we advance one more time, we've also used this to make tall electrospray emitters for a wafer sap project we're working on here. And so you can kind of see the aspect ratio of those. And if you advance to the next, we'll dive into those just a little more because they're fun. And so here's on the left, you can see where we've got sub-resolution features in the mask. It can be expensive mask sometimes, but it will thin down the resist in the shapes that you want when you get that right. And then in the center panel, you can see what the arrays look like. And then this electrospray material is fed up from the bottom in the holes between these thrust emitters. And if you look on the right, you can see that we actually texture the emitter surface so that you get the right kind of hydraulic wicking to bring the electrospray fluid right up to the tip where it's pulled apart and creates thrust through a field plate just above it with holes in it, with a high electric field in between the two. So that's interesting stuff we've done with our lithography. Now, if we'll continue, one thing that we have is that not many fabs do, certainly not many non-commercial ones, is ion implant. Some say real fabs have ion implant. We are really lucky to just be commissioning a new ion implanter. This is about a $4 million tool, and we moved it in at the end of February, and we almost got it started up in 2 months. We're not quite there. But as you can see, it's about 50,000 pounds in the lower right. It's got complex mechanics because, you know, these wafers are scanned in front of a beam with a twist and a tilt to get the ions entering at the right angle. We've got great dose and energy range on this. And so we're thrilled about having this new tool. We were limping along with an old tool for a number of years and had to send our work out. We have a qualified secondary provider, but FedEx processing is slow and a little expensive compared to having your own implanter. So we can advance. And another important differentiator for our facility here is defect management. Again, few non-commercial fabs have it. I think only in the US, us and Sandia. You can find tiny defects and complex patterns so that you can detect defect issues early, limit the yield impacts, means your cycle time for development, which is all we do in a prototyping facility. We only basically develop. And you can also predict your circuit yields. Once you get to know your defect density, you can figure out how big of a chip you can build and still get what kind of yield. Now, if we advance, we'll look at the elements in this defect management. And when you're trying to control defects, if you can do it in the lower left with your process tool, can figure them out, like fault detection and classification, that's great. We don't have a lot of that, but you can almost catch defects in real time once you've got the signals. Or you can do automated inline inspection optically, which is what we're doing. But if you wait till electrical test, it could take you months, and you've got a lot of work at risk before you realize what your problems are. So if you'll advance, we've got this KLA 8920 or Altair system. It's an automated optical inspection system that in bright field and dark field can scan a wafer in about 2 minutes after a couple hours to a couple days of recipe development. And what you get out of that, if you advance, you'll get a, you can image the defects based on the settings where you want to detect images. And if you advance again, you can get a map of where they are. Now we've got those maps correlated to our electron microscope. If you advance, ours at the moment is a Hitachi 7840 that can take in those maps where we can drive to those specific defects and identify individual submicron defects. And if you advance, that's fitted up with energy dispersive spectroscopy or EDAX, so we can see what they're made of in elemental composition down to like the % level. So see what they look like, what they're made of. And then if you advance again, that's what I was talking about, the defect composition. And now to take care of all this data, you generate tons of data. And if you advance one more time, in this graphic here, at the center of that is we have a defect analysis software and server system. Ours is by Onto. It used to be Rudolph Discover, but they got consolidated. And it takes in data from not only our optical tool, but our light scattering tool and SP1. And it provides a whole bunch of review abilities to look at defects and look at defects biographies that come and go. The optical inspection system was about $1.5 million 8 years ago, and the defect analysis software service system was about $500,000. So if we continue, we'll show you some of what we've gotten done with this. Here's the type of defects you can find. In the center of the picture on the left in the red box is a tiny little resistor defect. And I'll point out that that is below the surface. That's below the surface looking through transparent oxides. So that's a downstream reaction that happened. And in these multi-project wafers, we were having 7 million resistors per wafer, and we're finding individual 1 out of a million kind of defects like this. And on the right-hand side, these are the tiny little transistor gates we showed from the 193 nanometer lithography video. And you can see it's finding these things. Those are only 100 nanometers wide at the time we're looking at those. And we can find little bits that were broken off at the end of a transistor gate. So if you'll continue, so those are defects that we found. To what effect? On the left, you can see that over years on a certain technology, we can get our defectivity rates down. And for this digital superconducting technology that it's about, we were routinely meeting 90% optical screening yield. So, you know, you don't have to get rid of all the defects, if you can get to high yields, you can just screen out the few bad chips so you don't pass them on to your sponsors. In the center, you can get some pretty tricky defects. We had a couple of defect types that were in our aluminum metallization. In the center panel in the upper right, you can see that the aluminum out of our aluminum copper wiring stack was kind of dissolved out, and we were able to find those optically. And just below that, you can see in between layers, we connect our aluminum wiring with tungsten plugs, a tungsten damascene process. And that little box is highlighting where we had a little missing tungsten plug. So we can find individual little ones of those in the seas of hundreds of thousands of interconnect links in a test structure. And where we're going with that is we've got a very large imager program right now, working with the Department of Energy, a burst mode imager for very fast picture taking of a few frames. And right now we're making these 62 millimeter on a side imagers. It takes 4 reticles for each imager. And we're about to start one that's 142 millimeters on a side, and we'll take 9 reticles for each layer to stitch a giant sized imaging chip together. Next, please. So just in terms of activity levels, we're developing more than a new inspection recipe a day on this. There's a little error here. It's not 40 different mask sets in a given year. It's 40 different patterns that you do the defect detection on. A mask set can have 25 wafers in it, so we're not doing 1,000 masks a year. We're doing about 1 a week. We're inspecting well over 100, 150 wafers per day, and we're collecting about 5 million images a year. And so we've, taken 2/3 of the defects out of our digital superconducting. We've gotten rid of most of the niobium deposition large particles for that technology type. And we found a number of different important yield problems for our CMOS process and corrected them. So enough about defect management.
All right, so now we'll move on to the device technology nodes. So this section actually kind of almost has four subparts to it. So first we're going to go through the foundry prototyping capabilities, so the fab, the microfabrication. We'll do a deep dive into one of those. Then we'll cover the packaging and a deep dive into one of those. So let's proceed on to the fab process technology nodes. So in that video earlier that Dan so well narrated, they covered some of these. They covered the 90 nanometer rad hard CMOS. We talked about the integrated optoelectronics, trapped ion qubits are in here. In addition to the ones you've already seen on the previous slides, we also have the imagers, which Dan just spoke of. We have CCDs on one side, we have avalanche photodiodes on the other. We also have the superconducting digital logic that's in here, as well as the superconducting qubit circuits. And I'm not sure if that's an image of the fluxonium structure or not, but that's one of the superconducting qubits that we do that has noteworthy, extremely high coherence times. So that would be one of our technologies. In addition, so over here on the right, the GaN on silicon is actually done in the MEL facility, but since GaN's a compound semiconductor, it ended up on the right side of the slide. And then we have a whole array of different technologies. I think one of the things that should jump out at you when looking at the slide is just the wide diversity of applications and process technologies. Everything from additive, glass manufacturing. We even have the bottom right one, the microhydraulic actuator, so this micro machining technology. And this one was particularly noteworthy because of the remarkable power to weight and torque to weight ratios that it achieved. I think I hit everything on this slide. So now we'll dive into one of these applications. So SQUIL is superconducting qubits at Lincoln Laboratory. So this is the Qubit Collaboratory, which is a national quantum initiative. It was sponsored by the Laboratory of Physical Sciences. And you can see here, I think one of the key things it says, It aims to democratize access to robust, reliable qubit fabrication. And the way we do this is we have a release design kit that's supported by Lincoln Laboratories, established strengths in materials and fabrication and packaging and testing of qubits. Folks around the country are designing superconducting devices in our process, and we're able to produce these 8-inch multi-project wafers. So the wafer you see on the right is one of these. You can see it has like 7 columns and 7 rows per reticle field, so that's like 49 unique designs. And then it's got these long die. Those are TUPAs, which stands for Traveling Wave Parametric Amplifier, which is a device that's in high demand in that community. And I believe that was the original TUPA was designed by a student. So I also thought that was pretty inspiring. There's more information on a lot of the links embedded in this presentation as well. So, and also I think almost all of this is available on our website as well. I think on to the next slide. So now we're going to cover packaging. So our packaging technologies, we've got the electronics packaging capabilities on the right, on the left, and optical on the right. The big takeaway for me for this slide is that we got capability to do die-to-die, die-to-wafer, and wafer-to-wafer integration. So you have everything from your conventional wafer dicing, wire bonding, you've got bumping. I believe that one of the unique things, I'm not sure if it's on here, is that we are one of the few places in the world that have through superconducting through silicon vias, which is also noteworthy. And then on the right side of this slide, we've got the optical packaging capabilities, as well as in the bottom right, the smart fibers, the functional fibers. One thing that is, I think, is also clear when you see this list of technologies presented kind of all in one place is really there's a lot of non-traditional thinking afoot, especially in the packaging world. So a lot of 3D, whereas in the past things were much more 2D mindset, non-planar even, and some openness to novel techniques. So on to the applications. We'll do a deep dive. So this is it's 2023 R&D 100 award for quantum memory, and this was using silicon nitride integrated photonic circuitry to manipulate vacancies in diamond film. So with light, they're able to induce and also to write quantum states to vacancies in diamond, which is, I think, extremely exciting. So the application here was a quantum repeater, which is a highly desired packaging element. They need it to address the inherent coherence or actually decoherence challenges you have when you're transmitting quantum information. So this was really fantastic. There's a link to it there as well, to the whole paper. This was a Lincoln Laboratory team, I think cross-division even. And it's a great example of not only the specialty packaging, which is why it's in this section, but also of the photonics capabilities in the MEL. Because this is actually also the integrated photonics part of it is our process. I think moving on to the next slide, I have one more slide before I hand off to Dan. So our organization is extremely proud of our DoD trusted accreditation. It enables us to best serve our US government programs. And there really are 3 components to this program, right? There's the people, there's the materials custody, and there's the design security, or at least the IP security. So that all the people have to attain clearances, that the material custody is secured, that we have safe, so we have access controls. And the security as far as the IP is not only information technology security, it's also the restriction on photos being taken and those controls as well. It takes a huge amount of effort, and it requires a consistent commitment. We have a certified management system. And we spend a fair amount of calories maintaining and improving these controls because we see value in them. And you can see in the history here, 2015 is when we achieved the ISO 9001 certificate that was mentioned in Dan's bio. You can see that we expanded our certification to include packaging in 2017, and we expanded it further to enable multi-project wafers design aggregation in 2018. And I think that covers it. So now I'll hand back off to Dan.
The reporting aspect I wanted to point out is that MIT and Lincoln are concerned about climate change and working to reduce our carbon footprint and create technologies to help others do so. But what we could do internally, we were a very large energy user in the microelectronics lab. As you can see in the graphics here in the light blue and pinpointed on the aerial view of the Lexington site, I mean, we're the second largest user of energy for electrical use, and the second most dense energy user, Building F, happens to be a data center. So that's that's a little higher energy density, but we use more data because more energy because we're a little busier. So now if we break down on that, you know, about what the opportunity was locally, moving to the next slide. We've worked 3 big buckets that we looked at. First, we had different temperature set points in the clean room. For legacy reasons, you know, those were established 30 years ago. Who was talking about climate change then? Not enough, you know, in hindsight. But we were quite concerned about the process impacts. And so over the course of about 8 months, we got all our temperatures down to one uniform temperature because when the air gets recirculated up in that picture up in the fan deck, it mixes between all those different temperatures, and they end up fighting each other between the 52 recirculating fan units like you see in that center picture. But even there, we looked and we saw that we had some excess exhaust to get rid of. And now I'll drill down next onto a slide on the recirculation. We're changing that. If you could go back just for 1 second. But what we didn't get to yet on the right panel is our fluorinated gas abatement, and that I'm starting to estimate at about $2 million a year. But if you look for a very large site, it's about 5% of the total carbon footprint is just the emissions from our chlorofluorinated gases that we use. Almost all for cleaning PECVD chambers, and almost all traces down to just 4 deposition systems. So we could get 80% reduction, I think, if I can come up with about $2 million. For an abatement system. And we're talking to a company called Ecosys about a plasma abatement system where it does destruction there. Now, we already do have one abatement system, but it uses hydrocarbons to combust and degrade that. And it doesn't really feel right burning hydrocarbons to do abatement of gases to try to reduce your carbon footprint. So I look forward to pitching for those $2 million. But now back to the recirculation power. If you go to the next slide. What I'll point out is that we found out that we've been running our recirculation fans at a certain speed, the motor at 50 Hertz, which gives us about 60 vertical linear feet per minute flow from ceiling to floor. And our wafers stay nice and clean. In fact, we started seeing how clean our wafers stay, and we are leaving wafers out for weeks. And we're averaging 1 of the smallest particles we can detect per day per wafers left out for weeks. So we used that and we started turning down the fan speeds. And we went from 50 Hertz, 60 linear feet per minute to 40 Hertz and 50 linear feet per minute. And our wafers stay just as clean. And that saves us about $100,000 a year. And there's a lot of clean rooms out there that could probably turn down their fan speeds from legacy set points and save maybe 20% of the energy bill, which is where we're at now. And we might get up to 35% if the 40 linear feet per minute set point works, but we haven't quite tested that. So you can see some statistics in the center about the distributions we're comparing. Again, every point on those charts, the red and the blue, are wafers left out for a week to sometimes months. So there's a lot of observations there. And we even broke it down by those witnessing locations you see in the lower left, placements within our fab layout. we broke them into heavy, medium, and low traffic, and they're all fine. And so what this witness wafer testing does, it also tells us that our clean room protocols are working. Not just the clean room, but the people working inside the clean room are not getting the wafers dirty. So that finishes, I think, what we wanted to talk about, carbon footprint and climate reduction.
Right. So switching gears. So the last few slides in this deck are going to focus more on collaboration. Earlier we had the lab to fab slide where I had the 2D axis, and these images were on that as well. Now we're putting them side to side and actually going to talk about the relationship here. So we dive into kind of the important differences between the Lincoln Laboratory facilities and our brethren on the MIT campus. You know, we have the differences in our controls. They're much more flexible. They've got a lot of researchers using their tools to do lots of things with less restriction. They have much more open campus than we do as far as the security of the environment. So when we were talking earlier about being trusted, we talked about people, materials custody, and design security. The university campus doesn't have that, but we do. And then they're much more initial prototyping. So their emphasis is on feasibility and publication. We're more advanced prototyping. So we are, you know, our focus is more fielding usable articles, usable prototypes out of our fab. But that being said, the relationship between MIT campus and Lincoln Laboratory is seen as fundamentally important to realizing the mission for Lincoln Laboratory. We are part of MIT. We are what we are because of that relationship. And you can see in this graphic how you have the arrows, the fact that you have this connection back to MIT campus or to the university setting. The ideas and the people and the movement of those back and forth is vitally important to us. So this is one of kind of the foundational, you know, cornerstones of our collaborations is that we are part of MIT and part of that organization. Moving on to the next slide. There are other collaboration opportunities as well. So the vast majority of our work at the laboratory is from U.S. government sponsors and comes to us kind of through our prime contract with the U.S. Air Force, and that we refer to as on-contract work. There's also off-contract work, which might be with other entities from commercial enterprises to universities, other research organizations. And for that, we have several ways of working with people, various cooperative research development agreements, various collaborative ones, and test agreements. So things like CRADAs and test agreements are very common. And there are more than just those two. If you look at this slide, we have three kind of usage cases. The first one is kind of the most simple one. And this is where a facility wants us to run their material through one of our unit processes, essentially. The key thing here is that we're not doing any development of processes for this sort of work. We're just running our process on their material. And this would be most like a test agreement, and we'll get more into test agreements in the subsequent slide. The next kind of collaborative opportunity would be like designing into our existing processes. This is much more like the earlier slide when we talked about squill, where we have multi project wafers where people are designing in our process, and we're actually just doing the fabrication. So designing in the existing process, this could be CMOS, it could be our GaN on silicon, it could be superconducting digital circuitry, or like I just said, the squill or integrated photonics. In this case, again, this isn't a significant amount of new IP generation from these. So this generally there's a line here where some of this could be test agreement. Depending on the level of IP, it could cross into some sort of a CRADA or collaborative agreement. And then the last one here, joint process or device development. This is much more the generation of intellectual property. So here we're jointly working with an external party to develop technology. And so here our staff are actually not just executing, but actually developing as well. On to the next slide, we'll talk a little bit more about test agreements. So with the test agreements, kind of the key point, the key thing is that it hinges on the creation of intellectual property. So if our engineers are developing IP, then it can't be a test agreement. If our engineers are using established existing capabilities, then it could potentially be a test agreement. And a number of funding options are allowed when we're dealing with test agreements. And another key thing is that we can't be competing with industry. So those are kind of the constraints around us when it comes to test agreements. The next slide is an example of a successful test agreement. So this one is a company, it's a relatively recent test agreement. This is Apex Microdevices. They're an early stage startup. They are doing meta-optic technology for military space applications. They used our 193 nanometer lithography and pattern transfer capabilities to produce prototypes. And really this test agreement vehicle really enabled them to do validation of their process development on a commercially relevant tool set, right, our 200 millimeter tool set, and do it prior to commercial pilot production. So this really is an example of lab to fab being successful for, you know, this, hopefully when we do talk about lab to fab, and I know that this is a common topic now with all the CHIPS Act activities, it's incredible, it is key to have a facility that is both nimble and disciplined enough to bridge that flexibility, complexity gap that we had in that 2D construct earlier. The fact that we can span that allows us to do these test agreements for startups and allows us to do collaborative development with various sponsors. So I believe this is our last slide, and hopefully, all right, we'll finish on that note. So thank you very much.
Thank you, Dan and Carrie. All right, well, let's jump into the questions that we had come in. We actually had a handful, and if you did not get a chance to put in your question, it's not too late. You can drop those in the questions box. I'll start with the ones that came in first. So, are there any ongoing projects at the Microelectronics Laboratory that address current challenges in the microelectronics industry?
So the digital superconducting work that we talked about, where we were detecting defects, one of the big problems in the microelectronics industry is energy consumption. And if you don't know, I think 13% of all the US consumed energy is going to server farms now. And that's before AI puts it on steroids in a big way. And in fact, 1% of US energy last year was for mining Bitcoin. Anyway, that digital superconducting technology has, at the bit level, 5 orders of magnitude lower switching energy using a little magnetic bit rather than transferring an electron or a charge package. It's got to work at liquid helium temperatures, so by the time you take into the cooling, it's still 100 times more energy efficient per compute than current CMOS technologies are. And it also can run at higher clock speeds. Currently, all the silicon-based processors are capped out at about 4 gigahertz, and that's based on heat removal. But the digital SFQ technology can run up to about 100 gigahertz. And since it's superconducting, that doesn't create any extra heat. So that's one way in that we're working on microelectronics national problems.
That is amazing. Thank you for that, Dan. The next
another area, workforce development. That is something that is near and dear to my heart. 30 years in this industry, and I've just watched, you know, it get harder and harder to hire engineers in commercial fabs. So our role in our proximity to the New England hub. Hopefully, and I know we've got a number of activities going on, and also talking through with our friends in the Fab Owners Alliance and just the local industry here, trying to put together certification programs for process and equipment technicians for community college. That is something that is in the works and we're actively working on, and it's necessary.
Yes, that's
We also
wonderful. Thank
hire a
you.
lot of co-ops and interns, and that's been an area that we've spent a lot of energy on internally too. So that would be more to your undergraduates and you know, providing engineers to the industry.
Great. The next question we have is, what is the main reason for having your own fab instead of contracting through a semiconductor company?
Well, a lot of what we do, you couldn't do in a commercial fab at all. There's just no way they would be able to engage it. But Dan, maybe you have a better answer than I do.
The business model's different, yeah. So for-profit companies have a hard time with risk differently than we do. So we have a process committee process, and we take in new processes and materials, and that's part of our charter, is to try to get that done. But when some of these things take expensive or time-consuming mitigation plans to protect current technology capabilities, industry basically doesn't want any part of it. So there's a lot of stuff that industry is unable or unwilling to do, and that's where we fit in.
Yeah, the volumes just wouldn't support the expense for commercial fab.
Definitely understood. Thank you. We have another question. Any work on single photon detection at room temperature, specifically for VIS, NIR, and MWIR?
At room temperature, I don't know. We do a lot of avalanche photon detector work, both in silicon and in compound semiconductor, but I think they're all cooled for single electron. I don't think any of them operate at room temperature yet for to keep the noise down.
But we certainly have partners here at the lab who would entertain questions. But I don't think we're doing that right now.
Yeah, if I could forward that question, if somebody wants to get in touch with us, I can get you a more certain answer.
Wonderful, thank you. We had a lot of questions come in. You all's presentation was amazing. Does the fab support lithium niobate?
We are just about to install a lithium niobate etcher. So we do bonded lithium niobate, and it's an important part of our developing photonic integrated circuit program. So yes, we do. A lot of people are a little scared about what the lithium's going to do if it starts spreading around the fab, since it's a really energetic and almost kinetic little atom that can get in places you don't want it. And that's why the program sponsor is recently buying us an etching tool to segregate that. That should be come in May.
Oh,
And be running in
wonderful.
July.
All right. Is the burst mode imager faster than a DVS event camera?
I don't know, but we're partnering with Los Alamos National Labs on 2 different programs for 2 different facilities, and the end result is nuclear stockpile stewardship. So all I know is that it's a highly parallelized imaging set that takes about 8 pictures. I don't know how many microseconds between frames, but I don't think it's many.
Thank you. More on just partnership too. So how do other organizations work with the Microelectronics Laboratory at MIT Lincoln Lab?
Part of that question, Jamila?
Oh, did I get cut off? I'm
Yes.
sorry.
Yeah.
Yeah, I can repeat that. So more on just partnership opportunities. So how do other organizations work with the Microelectronics Laboratory at MIT Lincoln Lab?
So with our test agreements, they can be done directly through us. And that's again where if you want us to build something and you have the design and we have the capability. You define the process, we run it. That has the no entangled IP, and you can do those direct with Lincoln or through MIT.nano, who we partner with in a corresponding agreement. So that's the main way. But then on the other end, for entangled or co-developed IP, for commercial entities, we have a contract type called a CRADA, Cooperative Research and Development Agreement, that we do. So we have a basic template for that. And, you know, usually elements get negotiated before you sign them off. So at the end, they're individualized, but we have, you know, the boilerplate. We also have collaboration agreements that we use for academia and not-for-profit that are kind of fundamentally different. So we have a couple different ways to work with us that way. But both of those usually mean that we engage you with some of our technical staff to work on the development with you and partner. So that gets the co-developed IP, because we don't usually do a lot of process design within the Carrie and my operating group. We're really an operating group for the facilities, not so much a research and development group.
All right, and just a couple more questions here. What is your involvement with the CHIPS Act and ME Commons?
So we've been listed as a core facility during the Innovation Hub proposal stages with a number of proposing entities, and we ended up being a core facility for 3 of them. And the one that we know the best is the local one here, the Northeast Microelectronics Coalition, and that is administered by Massachusetts Technology Ventures, a Massachusetts state agency. And so that one, we've got a number of proposals that went in. Now, the proposals themselves were due at the end of February for specific project proposals. The 8 out of 81 Innovation Hub submitters were selected, and now those 8 hubs have submitted project proposals that were in at the end of February, and we expect to hear back next month or June to get in discussions about funding that we think actual project money would flow and project work would start in the fall. And so we hope to be working for more than one of the innovation hubs based on core facility partnering intentions that we've made.
Wonderful. And last question here from the audience. Is there any work being done on continuous variable photonic quantum computing?
I don't know. Everything, the types we've done here have been qubits. Yep. And really bit style, but not continuous variable that I've heard of, but I don't know. And if someone wants to forward that question through the channels, I can make sure we get a better answer.
Yes, thank you, Dan. I can make sure to forward that afterwards. All right, so regrettably, we're running out of time here, but Dan and Carrie, we extend a huge thank you for delivering such an excellent presentation. And please note that the slides and recording from today's lab showcase will be made available on the FLC website in the coming days. I also would like to extend an invitation for you to join us at the next of 4 upcoming MIT Lab Showcase series. You can find the registration in the chat, just pasting that here. And you can register for all upcoming lab showcases. Our next Explore Lincoln Lab Facility Lab Showcase will be an in-depth exploration of the Strive Center, and that's going to take place on May 21st at 2 p.m. Eastern. And just once again, a big thank you to Dan and Carrie, and I wish all of you all the rest of a beautiful day.
Thank you.
Thank you all.
Thank you, Jamila.
Bye.
Thank you, Adam.